Log on, tune in, find out. Another good idea from Cambridge.
Okay. I don't have to worry about this. Okay, thank you very much for the invitation to this nice conference here in this nice place. Actually, I must say I feel a little bit uncomfortable that I speak about photoacoustic imaging before Li-Hong Wang has given his talk. So he's really the experimental expert and also the first who did reconstruction formulas, which I'm referring to. So anyway, he can correct me afterwards, that's the advantage. So I will talk about something which it's maybe a little bit confusing, but the title Focused Illumination. And I will explain some of the experiments with our colleagues in Graz have done, where they somehow illuminate only parts of the object and then do reconstruction methods in photoacoustics. But first of all, I give some overview on photoacoustic imaging, and just referring to some of this article of Li-Hong Wang, and he says he describes photoacoustic imaging as the method of lightning and thunder. And I think this is a very good description which gives you which explains how photoacoustic works. So when you have when you analyze a specimen, usually we have very small things like zebrafish or something like this, so millimeter size. Then you expose them to a uniform illumination. So you expose the whole specimen to a lightning. And this is something which I'm referring to later on. In the beginning we were thinking just uniformly exposing the specimen to this lightning. But afterwards, later on, we will restrict it to some particular subsets of the specimen. Well, and you have already heard in Gunther Ullmann's talk yesterday that photoacoustic usually refers to visible or near infrared light, and thermoacoustics refers to when you excite with microwaves. So photoacoustic, after you have done this illumination, you visualize a little bit strange things. So the specimen absorbs the electromagnetic energy and it heats up, and then the heat is converted. For instance, since the material is converted, so the material expands, and when it expands, it reacts with sending out pressure waves. So there are actually 2 or 3 steps where the induced energy is converted into sound waves. And the imaging procedure of photoacoustic then is nothing else than measuring the pressure waves, presumably at the since it's non-destructive, at the outside of the object, and then to reconstruct the conversion parameter, which somehow converts the electromagnetic energy into the sound wave. So it's one parameter for many conversion steps. There have been many potential applications. Certainly this is not a complete list. Some of the exciting things, there are some breast screening which started with Kruger's work in already 15 years ago or even longer. Then there is the 20th mammoscope, which is led by Manohar. Then there are some exciting brain imaging techniques. Also there is an EU project which is called Adonis, and it's related to prostate imaging. So it's a very inspiring title. And then there are some other search where you do some gene research, which is, for instance, done by Rasansky, just to mention a few names. Also there is different potential applications of photoacoustic imaging. You can use it somehow as a microscope, where you scan into particular depths, and then you just scan the material parameters along a certain depth, and then you stack all the images together and create an image. So not many inversion techniques are used there, but it's just a scanning technique. And there is a nice PhD thesis from the ETH Zurich from Joel Niederhauser, where some of these experiments have been described. The things which we are using then is tomographic, because then you need some mathematical reconstruction algorithms, and the difference is just I think. Oh yeah. So the thing is just that the specimen, which is mounted in here, for instance, is rotated, and then you collect projection images, and then you do reconstructions from these projection images. And some of the things which I will describe later on are just in between these two images. So it's not really tomographic and it's not really microscopic. So let's go a little bit to the mathematical formulas. And the starting point for this, for photoacoustic imaging, is the 2D wave equation. In the standard formulas, the sound speed is set to 1, so normalized, and then you have just the classical wave equation, the simplest wave equation. And here I describe it as an inhomogeneous wave equation where you have the imaging parameter, which is later on this function f of x, and some excitation, which is somehow models the lightning. And what you actually recover then is a combination of multiple parameters. So I think you can model it differently, but you see that there is something which is the conversion of the heat into sound waves is somehow summarized by different physical material parameters which you cannot identify with these measurements, but you recover this function f, so a combination of these ones, usually. There's a different formulation because usually when the excitation of the electromagnetic energy is done by a laser, so you can assume that this function J models the laser, and typically it's very short, the excitation, so you can put in for this function J a delta impulse, which allows you to retransform this equation as a homogeneous wave equation with inhomogeneous initial conditions. So the initial pressure is then the imaging parameter, and the time derivative is put to 0 if you use here for this function J a delta distribution. So either consider the inhomogeneous one or the homogeneous one, it doesn't matter, as long as the excitation is modeled as a delta distribution. So this is what I said before. The imaging problem then is just measure something of the pressure outside of the specimen. Usually you put them into a water tank or something like this. If you do tomography, you don't have to, but well, this is what we are doing. And then you measure the pressure outside at the specimen. In the ideal case, which is the one which I will consider later on, you measure all around the object. If you do just partial measurements, it gets much more complicated from a point of reconstruction and stability. And then you image and visualize this parameter consisting of these several components of this parameter. Okay, so this is the mathematical model, and now I go into some of the things which you need to implement this imaging stuff. First of all, you have to define which measurements you take. And the standard way, and I guess this is the which most people do, is they use small piezo crystals like they're used in ultrasound, standard ultrasound also, for detecting the pressure waves. So usually these are considered as very small arrays, and in the reconstruction formulas later on, they are considered as points. So whenever you record a pressure at one of these piezo crystals, you consider this at a certain location over a certain time. So what we have done is, and I think it's mainly done in Austria, so we use typically large detectors. So for instance, here you see a very large detector, so this is not comparable to a point detector. So it's a very elongated object, and we measure. We also did some of these experiments, or not we, but the physics people. But so you measure the average pressure along this certain large array with this piezo film. So you don't get at each position there you get a pressure, but you get only the averaged thing. And somehow this was, when we published it in the first time, it was somehow controversial, because usually the reconstruction formulas were based on that the size of the array which is used blurs the reconstruction. So the interpretation was, if you use a very large array, then you get a very much of a blurring. But this is not the case if you use different reconstruction formulas. And the other one is that there are so-called line detectors, which are mainly optical methods. So you somehow, very naively, as a mathematician, I think I can say this, so you just measure the average pressure over this line, which is somehow visualized here in this water tank. So so you can either measure at some point data outside of the specimen. The specimen is inside here, so the light goes behind the specimen, so it's outside of the object. So you can measure at some points, you can measure at some lines, or you can measure at some areas, and use these for reconstruction of the material parameters inside. So these are some of the reconstruction which we, some of the experiments which we did. So this is here the laser, and the second laser just was to measure the pressure along the lines of this, well, to measure the pressure along lines. And this was somehow a probe which we were using. So you can imagine this, it's embedded a mouse heart, which was somehow to simulate the heart attack, and then it was analyzed with photoacoustics. Just to give you about the size of the specimen which we are visualizing. And this is one of the left one is a reconstruction where the full specimen, the full heart of the probe was illuminated, and this is a histology taken afterwards from this slice. And what you see, the heart attack is here, this black material. So the cells have been exposed to oxygen loss, and this you can see also here in the histology. So they are not exactly the same slices, but they somehow have been aligned so that you can compare them. But the heart attack is not the white one, but the black one. The specimen has been exposed to loss of oxygen. So there are several things which are currently relevant, I guess, in photoacoustics, and which are some of the research interests. So first of all, as this was already mentioned in Gunther Ullmann's talk yesterday, the standard photoacoustic model does not take into account variable sound speed. There has been mathematical studies how you can do this. It does not take into account attenuation. There are also people who have studied this. But the thing which interests me is that the specimen is illuminated, and also it doesn't take into account that it's variably illuminated, so that there are regions where you have more illuminations than in other regions. And actually I don't want to use really variable illumination, but I want to use this variable illumination for defining new reconstruction mechanisms. So what I will talk about now, and which is somehow the new thing about this topic, is that we, together with our physics colleagues, which is Robert Muster actually, mainly Robert Muster and Sibylle Grath from Graz, that they have decided to somehow develop mechanisms where you illuminate to some certain regions of the object, in particular just to slices. And I will show you on the next slide the transparency, how it should look like. So you can imagine that now the illumination is not focused to the whole specimen, but to just a very particular region. And we make a mathematical abstraction that we just do it to a slice or a plane, but actually it's much more complicated. It's somehow the interior of elongated hyperbola. So it's not, the model is not completely precise, but I think it's a very good first guess. And then you measure the pressure, and also here is some modeling things to do. We assume later on that we use point detectors, line detectors, or area detectors, but actually the current experiments are done with focused illumination, with focused detectors, so like curved arrays which somehow focus into the interior of the object. So there is still some additional modeling to do. The advantage of using concentrating the illumination to a certain plane is that you require less energy to illuminate this object. Usually when you heat up these objects, you have to prevent a certain increase of energy that the specimen is not destroyed. So this gets much more relevant, and we are working with zebrafish which are about this size, so it doesn't, if you heat them up for 100 degrees, they are gone. But I mean, it's much less sensitive. Okay, but of course you get certain artifacts in there because we don't focus directly to the plane, but to some certain shapes which we don't know really exactly, so you have some autofocus blur. But there are some physical experiments. I think Rasansky from, not I think, but Rasansky from Munich has done this with focusing point detectors, and Sibylle has done it with focusing line detectors. So you don't see it very well here, but these are slices of a zebrafish, so about a few millimeters long. This, so this is actually the thickness of the zebrafish, and so you scan the zebrafish from the fins to the head, and here you see the head, and this should somehow part of the, somehow here are fins, for instance. So you from top to the, well, actually from what's the fin to the, it's a fin, from the fin to the head of the zebrafish. It's not everything is represented. So, but and I will show you some reconstruction formulas now for this sliced imaging. But I have to confess, this has not been done with these reconstruction formulas. The reason, first of all, the reconstruction formulas are too new, and secondly, they use focus detectors, so it's actually still a certain modeling which has to be taken into account. So now I come to the mathematical model, and the mathematical model is that I assume now that the imaging is focused to a slice, to a plane. So what I assume now is that the function f, which I want to image, can be written as a function of two variables in the plane, and the excitation is taken into the z coordinate. So it simplifies now to a certain way of three-dimensional functions where the z component is a delta distribution, and this just means that it's all illuminated just to a plane. And well, and then you have the imaging problem. Here nothing happens then as before, so it's still the same wave equation, normalized to the wave speed is normalized to 1, and the initialization is now the two-dimensional functions times the delta distribution. And so what the goal now of this focused illumination is to recover the function f. So in this case I only need to recover the function f hat, so the two-dimensional function, from certain measurements, and so I have to only collect 2D measurements somehow at the boundary over the time to reconstruct the function p. To reconstruct the function f hat. So it's not a three-dimensional problem anymore, but a two-dimensional problem. So now there comes a technical slide because we need to do some reconstruction formulas later on. All what I assume now is that the measurements are taken at the boundary of an object. Here it's an ellipse, and I do a different parameterization of the curve. So I take here some angle, which I call here which I call here theta, and with the angle theta I associate the tangent point. So this works for strictly convex functions. So I take this theta and I take this theta, and the parallel vector is the normal vector to the tangent then. So with this theta I can reconstruct the tangent point if the domain is strictly convex, and I use this then to derive reconstruction formulas for arbitrary domains. So this is somehow the thing which we keep in mind. If it's a sphere, then it's simple. Then this tangent point is just associated with the normal vector. It's the same as the cosinus theta sine theta. So if you forget about the general geometries, it's just identify this function c of theta just with this c of theta, just with this angle theta. So measurements are then taken in the three-dimensional domain. You can do three-dimensional reconstruction by doing it on every slice. So in the z component, but you can only every time you can restrict it to a two-dimensional domain. So this is now the figure. So and now we come to the measurements which we take. So there are several possibilities which I mentioned already, which are from classical photoacoustic. You can measure point detectors, which is maybe somehow not the conventional numeration, the standard way. So you measure just the pressure. So I normalize everything to the zero plane, because I do it just in one slice, and this is denoted by 0, and this is the function, the point where I evaluate. So just think of surrounding the object, and then I measure the pressure over time. So and the problem which I will face afterwards is reconstruct the imaging function, the function f, from these measurements all along this object. And then you can use other methods, for instance vertical line detectors. So you illuminate in the plane and you measure the average pressure along lines in this direction to the object. You can use vertical plane detectors, so you illuminate in this direction and you shift now planes along, or you rotate planes along the object. And you can use the last one, horizontal line detectors. This is actually where the images have been shown later on. So you have a line detector which is in the same plane as the illumination. So now I derive reconstruction formulas for all of these 4 cases. And first of all, illumination in this plane, measurements with line detectors in orthogonal or vertical. And so the trick which you always do in these cases is that you reparameterize the reparameterize the wave equation. So you make an average pressure in z direction in the third component. And when you do this, the auxiliary function, which averages the pressure in z direction, satisfies again a wave equation. But this is now a two-dimensional wave equation. So this is now a two-dimensional wave equation where you just do it in the R2 plane.
There's no z. Yeah. Laplace is no z.
Laplace is no z, I guess, yeah. This is correct, yeah. Just to be. Should get rid of it. Copy and paste there. Okay, so this is then the two-dimensional wave equation, and with these initial conditions. And now we have this data now, which is parameterized now with respect to the S1. but here you have in the boundary of the convex domain. So this is on the boundary, it doesn't work. And this is the angle, let's say this is the angle and this is the point of tangency, which is uniquely determined if the function is strictly convex, or if the boundary is strictly convex. So, well, and then you can reconstruct reconstruction formulas, but they are very much dependent on the geometry which you are using. So you can use half space, so you measure the boundary of omega. Omega is the half space, and the boundary of omega is just the coordinate axis. Then you have you can do it along a circle, and I guess which has not been known so far is that when you do it along an ellipsis. But these are the same reconstruction formulas which you actually can also reconstruct from inversion of the spherical mean operator, which are already published in Linzer's work in the 80s, or Norton and Linzer in 81. So I just summarized this, how they look like. So the formulas get somehow a little bit complicated, but they are explicit. If you do the half space, then it's just a convolution, how to derive the function f hat. So you have this convolution operator here, and this is just the data. So that the data means just that it's these vertical lines which you are integrating, and then you plug it in, and then you convolve the problem, and you get this with this somehow nasty kernel. So it's a cosine times the exponential function. It's the only formula which we have from these three, which is an formula of Fourier type. All other ones are exponential series, and I guess the reason is just that the half space is unbounded, that you don't get series expansion, but Fourier expansion. So if omega is a circle, you get somehow almost these formulas like in Norton and Linzer, but they used actually a certain problem of ultrasound tomography, which they reduce to the inversion of the spherical mean operator. So this is the connection, that everything can be reduced to the spherical mean operator after some transformation, and this is why these formulas are so close, but I think the physical model is completely different. So here it's again some sort of convolution, but instead of the Fourier integral, you have here now you have somehow a series expansion where the Bessel function comes, and these Bessel functions just come because you use spherical coordinates. So, but essentially it's again a convolution problem with well, somehow complicated kernel, but you have an exact reconstruction formula inside. If you do it in an ellipse, and I guess this is somehow a rather new formula, the thing is it gets again of the same type, a kernel function with some functions r. Don't confuse it with this r. This is the boundary, which is the parameterization of the ellipsis. So the ellipsis has axis r times cosine hyperbolicals of r naught and sine hyperbolicals. So it's not the same r as this function here. The functions r and phi are the Mathieu functions. So these are the functions which satisfy these elliptic differential equations, where you have here a function sine squared inside. So, and the function r, which popped up on the right hand side, you mentioned, if you recall it, it's a product of the functions phi and r. They are the solution of this equation. So it's a sine hyperbolic. I don't know how it's called in English, but sine hyperbolicals. Now, okay, so this is essentially for all of these geometries. You can derive in the 2D case exact reconstruction formulas. If you restrict yourself to geometries which are circles, half spaces, or ellipses. Now if you take vertical plane detectors, somehow you do the same trick, but you integrate now along, you average now along planes, the function, the pressure function. And if you do the averaging along planes, you derive a one-dimensional wave equation. So the average satisfies now a one-dimensional wave equation for each component theta, which is the plane, and for each radial component, which is considered variable then. So you average over all planes, and this satisfies then a two-dimensional, a one-dimensional, well, two-dimensional with time and a radial component. But it's a trick, the same trick as before, not integrating along lines, but instead integrating along planes. And then you derive that this function for fixed angular component satisfies this wave equation, the one-dimensional wave equation. Initial condition is the measurement data, which is averaged along planes, and the partial derivative is 0. So, and then now you can do reconstruction formulas. The reconstruction formulas is first use D'Alembert's formula, and then you take a Radon transform to reconstruct the imaging function, this hat f, from the measurement data. So first D'Alembert's formula and then Radon transform. And interestingly enough, this approach works for every convex geometry. So it's, I think, a very nice way to measure it. And if you restrict yourself, if you don't want to restrict yourself on certain measurements, geometries, this is the approach to go, because then you need the reconstruction formulas are exact for every convex domain. With point detectors, it's actually one of the most complicated things, but still very elementary. You measure the pressure. You express the pressure formula with the spherical means. This is still 3D. Then you parameterize the boundary of the spheres, and then if you use this parameterization, the function f now is composed of the two-dimensional functions times the delta distribution. And if you integrate out the delta distribution, you get these formulas. And what you see here now is you have the relation between the pressure and the two-dimensional spherical mean operator. And once you are aware of these reconstruction formulas, you just have to integrate your measurement data with respect to time, and then use inversion formulas for the spherical mean operator, which are available again for special geometries like the half space or the circle. So horizontal line detectors. This is again now I integrate along the tangents and derive an equation for the averaged pressure field. This is again a two-dimensional wave equation now. For fixed angular component, it's the second time derivative, and here you have this radial component and the z component, which is now really in the direction where I don't reconstruct the function itself. So, and then the problem has to be modified a little bit. These these averaged functions along the tangents can be written in this form. So you average the initial imaging parameter along these lines in the illumination plane, and these form then the illumination conditions. So instead of having here the function f hat itself, you have the averaged along lines, but still the delta distribution. So it's still a three-dimensional problem at this point. So, and then, well, there's a certain things which you have to do. You plug it into the standard reconstruction formulas, which I already showed in the beginning. So this is the same as using the spherical mean operator, but now with this special illumination condition at the beginning. And then you do the same as before. You integrate out the delta distribution, and get out again a nice formula for the, well, I should say it's a nice formula, but you get out a formula for the averaged imaging function along certain directions. So this is now the reconstruction formula. Again, as before, you have to first integrate the data and then use, this is an integral equation which is of Abel kind, where you have an exact reconstruction formulas for the integral operator, and then you apply now a one-dimensional Radon transform, you get this function f theta. So the only thing which is different is that you have a certain Abel transform in between these two functions to the previous one to get the reconstruction formulas. So, well, if you are interested how the Abel transform looks like, it's written down here, but it's just that you express the data in terms of the Abel transform, which is written down with this A here. And then you have an exact reconstruction formula because you can invert the Abel transform exactly. So the conclusion of my talk is that I have shown you some reconstruction formulas when you have some focused illumination, when you illuminate to a plane. And something what was surprising for me in this work was that for several measurement devices with integrating detectors, you can develop reconstruction formulas which are exact for every convex geometry, which was not the case in photoacoustic before. Okay, thank you.
Questions, please.
With these reconstruction formulas, do you have any idea, or can you estimate at all how those formulas may vary, or how the results may vary, have small changes, as you say, from your data? What happens, I'm saying sensitivity on measurement.
We have not investigated this, but since you decompose it into usually Radon transforms and Abel transforms, the only things which you have to look after is the formulas, the stability formulas for the Abel transform, which there are some, and for the Radon transforms. But I have not done it precisely. But I think if you decompose every step, you can derive the stability estimates.
Other questions? Yes, please.
Otmar, have you thought about building arrays of line detectors or plane detectors?
Well,
so just to speed up the data acquisition.
Yeah. So what they have built now, but this has not been implemented in the formulas. They have now these arrays of line detectors. I think they have 64 arrays of 64 lines. But I have not seen data with this stuff so far.
It still requires rotation, right? Even with array.
Yeah, I mean, if you do it in this way, tomographic, I think we still have to rotate it. But maybe you can use it for focusing, then you use it in a sort of microscopic mode. But all of the physics, I guess, in Graz they are doing tomographic, they're just rotating it. But I think the more practical way is definitely to do some microscope.
Other questions? Well, thank you very much, and we have a break till 11.